intricate. Maybe picturing a huge building, loads of levels, rooms everywhere.
Yeah.
It feels almost impossible to know where anything is.
Yeah, definitely.
Well, today we're kind of handing you the blueprint, not for a building, but for something way smaller, yet it's the foundation of, well, everything, the atom.
That's right. And we're going to really dig into how electrons arrange themselves,
Mhm.
specifically atomic shells and orbitals.
Yeah, we've got some great material here that lays out how these tiny, tiny electrons get organized around the nucleus.
It's surprisingly orderly, actually, almost like, Russian nesting dolls. You've got the main shells,
Okay.
then inside those, the subshells,
Subshells.
and then tucked inside those are the orbitals.
Gotcha. So our mission today, for you listening, is to get beyond just sort of knowing the terms.
Right.
We want you to really understand how they fit together. Because honestly, this is where it gets super interesting, this abstract setup. It's absolutely key to understanding how atoms connect, how they form.
Everything you see, touch.
Exactly. Hopefully, a few light bulb moments ahead.
Okay, so let's tackle this hierarchy. That building analogy you mentioned, it's actually pretty good.
Oh, yeah. How so?
Well, think of the atomic shells, electron shells, as the main floors.
Okay, floors.
They represent the principal energy levels, basically where the electrons are most likely hanging out. Higher floors mean more energy, further from the ground floor, the nucleus.
Right, right. And then on each floor, you've got apartments. Is that the next step?
Exactly. The subshells are like different types of apartments on each floor. They define the general shape of the space where you've got a high probability of finding an electron with a certain energy.
Shapes.
Okay.
And inside the apartment?
Individual rooms. Those are the atomic orbitals. Very specific 3D regions where there's a really, really good chance, like over 90% chance, according to one source of finding a particular electron.
Over 90%.
Oh, wow.
So it's not like a tiny planet orbiting, more like a fuzzy cloud.
Precisely. It's about probability, not a fixed path. That classical model just doesn't quite cut it at this scale.
Okay, the building analogy is sticking. Let's zoom in on the floors then, the atomic shells, the main energy levels.
Right. We use the principal quantum number, n for those. N1 is the first shell, n is 2 the second, and up it goes.
You also hear letters sometimes, right? K, L, M.
Yep. K is N1, L is N2, M is N it's 3, and so on. It's just another way to label them.
And higher N means higher energy, further out.
Both. Higher N, you're further from the nucleus, and the electrons in that shell generally have more energy. Like climbing stairs takes more energy to get to the higher floors.
Makes sense. Okay, floor's done. Now, the apartments within those floors, the subshells.
Right. These are defined by a different quantum number, the azimuthal quantum number. We use the letter L.
Okay.
And the possible values for L depend on N. For a given shell N, L can be anything from 0 up to N1.
Ah, okay. So it's linked to this shell number.
Directly linked. And each value of L corresponds to a different shape of subshell, or rather the orbitals within it. We use letters for these two.
Letters for shapes, like
So if L is an S subshell, think spherical, it just contains one orbital.
bills for spherical. Got
Right.
it. What about L1?
L1 gives you a P subshell. These orbitals look more like dumbbells.
Dumbbells.
And there are 3 of them in a P subshell. Each one is oriented along a different axis, X, Y, or Z. So we call them PX, PY, PZ.
3 dumbbells pointing different ways.
Mm-hmm.
Does that orientation, matter when atoms meet?
Oh, absolutely. That spatial orientation is crucial. It dictates how atoms can approach each other, how they can form bonds. It really influences the final shape of molecules.
Huh. Interesting.
So
Okay,
cool.
so S is spherical, P is dumbbell. What comes next?
L2. L2 takes us to the D subshells. 5 orbitals here, and the shapes get, more complex, kind of clover leaf-like, some of them.
5 d orbitals and L3.
That's the F subshell, even more intricate shapes, and there are 7 F orbitals.
7. Wow. Okay, so SP, DF, 1, 3, 5, 7 orbitals.
You got it. And notice the pattern. A shell N has exactly N types of subshells.
Oh, right. Shell N1 just has SL0, shell N2 has LZ and PL1.
Shell N3 has LZ0, PL1, and DL2, 3 types. Perfect.
Nice. Okay, so we've got floors, shells, N, apartment types, subshells determining shape. Now the specific rooms, the orbitals themselves.
Exactly. These are defined by the magnetic quantum number, NLL. It tells you the specific orientation of an orbital in space.
ML. Okay, another quantum number.
Yep. And its possible values depend on L. ML can range from LL all the way up to plus L, including 0.
Okay, let's test that. For SL0, so ML can only be.
0. Just 0. That's why there's only one S orbital in any S subshell.
Makes sense. For P, L1, so ML can be -1, 0, and +1.
Precisely. 3 possible values corresponding to the 3p orbitals, px, pi, y, pz, with their different orientations.
It connects. And for dl2, so L would be -2, -1, 0, +1, +2.
Exactly. 5 values, 5d orbitals.
And F, L3, 5. 3, -3 to +3. 7 values, 7 F orbitals. Got it. There's also a little formula, right, for the number of orbitals.
Yeah, a simple one. The number of orbitals in a subshell is just 2L plus 1. Works every time.
2L plus 1.
Whoa.
So, okay, wrapping this bit up, N gives the shell the main energy level.
Right. The
So
floor.
L gives the subshell type linked to the shape.
The apartment blueprint.
And M gives the specific orbital its orientation.
The specific room number and layout. It's like a complete address for where an electron is most likely to be found within the atom's building.
A quantum address.
Yeah.
Love it. So now we have these rooms, these orbitals. Can you just cram as many electrons in as you want? Are there, like, occupancy limits?
Great question. Absolutely, there are limits. A really fundamental rule comes into play here, the Pauli exclusion principle.
Pauli exclusion.
Yes.
Sounds important.
It is. It states that any single atomic orbital can hold a maximum of 2 electrons.
Only 2.
Only 2. And if there are 2 electrons in an orbital, they must have opposite spins.
Opposite spins. What does that mean?
It's another quantum property called spin. Think of it sort of loosely, like the electron spinning on its axis, creating a tiny magnetic field. It can spin one way, which we call spin up, plus 12, or the other way, spin down, negative 12.
So 2 electrons in the same orbital room have to be spinning in opposite directions.
Exactly. You can't have 2 electrons in the same atom with the exact same set of 4 quantum numbers, N, L, Ml, and the spin quantum number, Ms. At least the spin has to be different if they share an orbital.
Okay, that makes sense. And that limit, 2 electrons per orbital, that must affect how many electrons can fit in a whole shell, right?
It absolutely does. We figured out the number of orbitals in a shell N, remember?
Was it N squared?
Spot on. N squared orbitals in shell N, and since each orbital holds a max of 2 electrons.
Then the maximum number of electrons in shell N is just 2 times N squared.
Bingo. 2 and a no, that's the max capacity for each shell.
Okay, let's walk through those examples again, but with the electron capacity in mind. Shell N1, the K shell.
Right. N1 can only be 0, so that's just the 1's subshell.
And L0 means LO can only be 0, 1 orbital. The 1's orbital.
Yep. 1 orbital, max electrons.
2 electrons, because 2 times 1 squared is 2.
Perfect. That's why hydrogen has 1 electron in 1s, and helium has 2 filling the 1s. The first shell is full with helium.
Okay, shell N2, the L shell.
For N2, L can be 0 or 1.
So we have a 2 subshell and a 2p subshell.
Correct. The 2 subshell, L0, has 1 orbital. The 2p subshell, L1, has
3 orbitals, px, p, y, pz, because ml can be -1, 0 plus 1.
Right. So total orbitals in the N2 shell?
1 is plus 3 p's. That's 4 orbitals.
4 orbitals total. Maximum electron capacity.
Using the formula, 2 times 2 squared,
Yeah.
2 times 4 is 8 electrons.
Exactly. So the second shell can hold up to 8 electrons, 2 in the 2's orbital, and up to 6 in the 3 2p orbitals.
This increasing number of subshells and orbitals, N gets bigger. That's why the outer shells can hold more electrons.
That's precisely it. More energy levels mean more available subshell types, which means more orbitals, allowing for more electrons overall, more apartments and rooms on the higher floors.
Okay, one more. Shell N3, the M shell.
N3, possible Ella values.
0, 1, and 2, because L goes up to N1.
Right, so we have 3's, 3p, and...
3 subshells.
Yep, how many orbitals in each?
Okay, 3L has 1 orbital, 3P-L1 has 3 orbitals. 3L2 has, ML goes from -2 to +2, 5 orbitals.
Excellent. Total orbitals in the N3 shell.
1 plus 3 plus 5.
Yeah.
That's 9 orbitals.
9 orbitals, max electrons.
2 times 3 squared. 2 times 9. 18 electrons.
You've got it. The third shell can hold a maximum of 18 electrons.
So this whole structure, shells, subshells, orbitals, the rules like Pauli, it's elegant, but it's not just, theoretical bookkeeping, is it? It must have real-world consequences.
Absolutely. This isn't just abstract quantum mechanics for its own sake. This electron structure dictates everything about how an atom behaves chemically.
How so? What's the key connection?
It really comes down to the electrons in the outermost shell. We call those the valence electrons.
Valence electrons. Heard that term.
They're the ones involved in forming chemical bonds. An atom's desire, so to speak, to gain, lose, or share these valence electrons to achieve a more stable configuration, often like a full outer shell. That's what drives chemical reactions.
So it's all about those outer electrons wanting stability.
Pretty much. That simple count and arrangement in the outermost shell. It explains why, say, sodium is super reactive and neon basically does nothing. It's the atom wanting that stable state.
And this connects to the periodic table too, doesn't it? I remember something about groups.
Directly. Elements in the same vertical column, the same group, have similar valence electron configurations.
Meaning same number of electrons in their outer shell arranged similarly.
Exactly. Same number, often in the same types of subshells, S or P usually. And that's why elements in the same group have such similar chemical properties. They have the same tools, the same valence electron setup for interacting with other atoms.
That makes so much sense why the table is arranged that way. It's reflecting this underlying electron structure.
It really is. The table is a map of electron configurations in a way.
And you mentioned earlier the orbital shapes, like the P dumbbells, influence molecular geometry.
Crucially, we're not diving deep into bonding theories today, but yes, the specific shapes and orientations of atomic orbitals, especially S and P, directly influence how they can overlap to form bonds, and therefore the final 3D shape of the molecules they create.
Wow. So understanding these orbitals is step one to understanding why water is bent and methane is tetrahedral.
Exactly. It all stems from this quantum mechanical description of electron probability distributions. Grasping shells and orbitals is genuinely foundational. It's the bedrock for understanding the building blocks of, well, everything.
Okay, so let's just quickly recap for everyone listening. We've gone through this amazing hierarchy inside the atom, starting broad with shells, the main energy levels.
Orange floors.
Then zooming into subshells, defined by L, related to shape.
The apartments.
And finally pinpointing orbitals, specific regions, L, specific orientations.
The rooms.
All governed by these quantum numbers, giving each electron a unique address, and limited by the Pauli principle, max 2 electrons per orbital, opposite spins.
You've nailed it.
Wow.
And what might seem, maybe at first glance, a bit dry or technical,
Yeah, lots of letters and numbers.
is actually the absolute foundation for understanding why matter behaves the way it does. All the diversity, all the reactions, it starts here.
Right. So here's something to maybe chew on after this, a provocative thought for you.
Okay.
Think about how these abstract rules, these quantum numbers, shells, probabilities, how they ultimately lead to the tangible world.
Yeah.
The hardness of a diamond, right? The fact that sodium explodes in water, the incredible complexity of a DNA molecule. It all traces back to how the electrons are arranged according to these fundamental principles.
It's a pretty staggering connection when you think about it, from quantum rules to the reality we experience.
Definitely. Maybe check out some of those resources mentioned, like Khan Academy or BYJUS,
Yeah.
to visualize it more.
And, having this foundation, it's going to be incredibly useful for understanding other related topics we might explore down the line.
For sure. This is bedrock stuff.